Incised valleys may work in low to intermediate accommodation settings. As everyone in this room would be aware, incised valleys are key hydrocarbon reservoir types in the Western Canada sedimentary basin, especially when we consider our heavy oil resources and our deep basin gas reserves in the basin. What I'd like to do in the next 45 to 50 minutes is step back a bit from the mechanics of how we go about correlating incised valley systems, but instead focus more on the context of how and where incised valley systems fit in a foreland basin setting, the style of the channel patterns that might develop, and thirdly, the techniques we can use to differentiate between different channel types. To do that, I'm going to focus on the Jurassic and Lower Cretaceous basal quartz and its stratigraphic equivalents in southwestern Alberta by placing it into the context of the foreland basin model. So the outline of the talk, it will be a brief introduction. I'll go into describing the foreland basin and drainage patterns, the application of such to the Western Canada foreland basin, and describe a couple of new some concepts, what an underfilled versus an overfilled foreland basin is, and the amount of cyclicity that can occur within these types of deposits, how accommodation controls these units, the amount of space we have, then deal with some key techniques as we go along, and then sum up with some summary and conclusion statements. And basically what I'm trying to do is, just like a nested set of dolls, show you how each of these pieces fit one into the other. As we're aware, the Western Canada sedimentary basin has a pre-foreland basin component that occurred until about 170 million years ago. And then in the last 170 million years, we had continental collision off to the west, and we had the development of a foreland basin. And in that foreland basin, there's a number of different stratigraphic units that were deposited within this basin. And I'm going to be concentrating in this portion of the stratigraphic record here on the basal quartz section of the unit. Now, the foreland basin in North America extends from the north to the south along the eastern margin of the foothills, where we have subduction and accretion in through there. We basically have two different styles of foreland systems, and I'm going to be concentrating on this one over here, the Retorock foreland basin system. And if we take a look at what's happening within that foreland basin system, on the most gross scale, it can be broken up into four components: the wedge top component, immediately on the other side of the thrust front, the foredeep, the forebulge, and the back bulge area. Now, if we're taking a look at a foreland basin system, we can think of it as occurring in two different end members. One of them is the underfilled foreland basin system, where we only have the foredeep, then we have a drainage divide, or the forebulge, and then we have the craton located in through here. In an overfilled foreland basin, we have an additional unit called the wedge top that occurs in this position here, and we may or may not have deposition on the forebulge, and we have another low area here before we get to the craton called the back bulge area. And the reason why I'm going into this type of detail is we're going to see that the different drainages that occur in the Lower Cretaceous are unique to each of these individual depositional systems or areas. And when we take a look at it, what's really controlling the type of depositional system we have is which source area we're tapping within the foreland basin system. So in an underfilled foreland basin system, in the wedge top area of the basin, our source is coming off the hinterland, off the mountains, and coming in in this direction here to an axial drainage system that goes along the foredeep, where as in an overfilled foreland system, this hole is now filled up and the sediment that is coming from the mountains can continue along and go all the way out to, in our case, to the east. We go across an area where you have a drainage divide and you may have a unique drainage system operating off to the unit. So a spoiler alert would be that the basal quartz packages are found within the wedge top and the foredeep area, whereas the McMurray is found within the back bulge area located in this area here. Now, it's not just this simple model that DeSelles and Giles put together back in '96. A long strike along the length of the foreland basin, there's a series of compartments. There's compartmentalization, and there's a unique change in depositional gradient going from landward to seaward within these areas. And so we're going basically from fluvial and non-marine types of deposits in this position here to more open marine type of deposits along a number of these different types of units. So that when we take a look at the model itself in through here, we basically have areas in the underfilled where we have axial drainage. The circle represents drainage coming in and out of the screen, with the majority of the sediment coming in this case, off the mountains, off the thrust front, coming in from, in our case, from west to east, and a smaller amount coming in from east to west. Whereas in an overfilled department system, especially at the beginnings of it, we can have multiple paleo drainage systems, each of them having both source material coming in and out of the screen and material coming in into it from either side of the unique drainage. When we're dealing with the Western Canada foreland basin system, we have to think about what scale that we're dealing with. So this is a well-used diagram from Kaufman, modified from Kaufman in '84, which basically shows you the geometry, the asymmetric geometry of a foreland basin. And this represents the different stratigraphic units that are filling it. And we have certain units that fill within axial drainage and certain units that fill because of transverse drainage coming in. On the grossest scale, we're dealing from fluvial to fluvial estuarine to nearshore deposits and then offshore deposits. There's a big change in, there's a 90-degree shift in the orientation of the major depositional systems that go along in through here, right? So the fluvial system will go in one direction, and then 90 degrees to that, we'll have the shorelines and then the marine deposited. So in the axial drainage units in through here, they're running from south to north, with the shorelines running basically east-west on the gross scale. And that's what's happening in the underfilled portion of the foreland basin from the Jurassic up to the Manville. In the overfilled foreland basin at the grossest scale, we're dealing with transverse drainage, and the incised valleys and the valley systems are running from west to east, with the shorelines running from north to south as you go along through that. Some examples of this type of geometry. This is work done by Miles and Hubbard from the U of C, taking a look at the underfilled foreland basin associated with the Niconassin. And their paleogeography in something like this basically shows the axial drainage going from south to north, going from fluvial to deltaic to marine. In a position like here, that's where we would have the forebulge. And so what we're dealing with is axial drainage going in this type of direction. That's in the underfilled foreland basin component. In the overfilled foreland basin component, this is work done by people like Plint and Wadsworth and Bhattacharya and others. And you see in the Dunvegan, the Incised Valley systems running from west to east with a north-south paleo drainage system. So that's what's happening in those types of units. If we were to concentrate on what's happening with the latest, most Jurassic to the lower Cretaceous, that's the type of geometry that we have in this system over here, where this is from Bloom and his work that was based on paleo drainages associated with detrital zircon mapping and heavy mineral mapping. You can see that in this white circled area in through here, we have a number of paleo drainages that are sourced in the foothills and then move from south to north in this position here. Whereas we have this big green area located here, which is basically running sediment from the east and the south and the west into a series of trunk systems that move towards the north. That's the McMurray paleo drainage system as you're going along. There's different paleo drainage systems associated with the lower to middle Cretaceous. And because of that, one would expect as you went along that the mineralogy would be very different because the source terrains are very different between these different types of units. By the time we get into the Eocene and the Paleocene, the craton is in an overfilled state. And instead of having drainages in this area going from south to north, we're now having drainages going from west to east. And so that idea of that big change in orientation of the paleo drainages come together. Now, you can take that data and begin, or take that understanding and begin to do more detailed work on these types of units. So this is some work done by Horner and their co-authors back in 2019, again, taking a look at different types of detrital zircons and different types of heavy minerals. And they were able to see that just like in the Bloom study, there was an area of units located over here that are running from south to north. And there's an area here, a couple of drainages that feed into the McMurray system that come into this area through here. The paleogeography and the mineralogy and the stratigraphic framework that's associated here has nothing to do with what's happening with the McMurray drainages, because we've gone across a paleo drainage divide, a forebulge that's in this position located in through here. And we're going to be concentrating, therefore, on this lower box in through here when we get into the details. This is a map that was originally done by Kant and Abramson, taking a look at the isopac of the lowermost Cretaceous in Manville. And the darker the color represents more isopac thickness as you're going along. And arbitrarily, we took breaks at 80 and 120 meters of thickness. And we could see that as we go in this area here, this area in the BQ, we go from low to intermediate to high accommodation. And that will become important as we go along. And the question is going to be, what is controlling that change in thickness? Now, in the past, we've done some detailed work, and I'll talk about that and the people who were involved in that a little bit later in the talk. But this is just an example of one of the paleogeographic maps that we would pick up. This is going from Township 1 to Township 40, from the Saskatchewan border over to the foothills. This is the US-Canada border here. Each of these little black dots represent a well. Every two townships, we build a cross-section. Every 5 ranges, we build a north-south cross-section, and we would log all the cores that are associated with that, with those cross sections. And we would take a look at different internal stratigraphic units that I'll break into in a few moments. And then we'd map out the paleo drainage that's associated with these different units. And that's what the colored zones represent. These are the incised valleys that we see. This is for a specific interval called the BAT, the Bantry Alderson Tabor sandstone. And you can see quite clearly the tributary network that's feeding the trunk system that goes along through here. You can also see that there's a major shift across this dashed line in terms of the orientation of the trunk river system. You can see that there's a break in this position here, which we call the zone of flexure, and that the paleo drainage on the other side of that is actually going away from this topographic high, this zone of flexure. So there's two different drainages. This zone of flexure represents the forebulge. This is a paleo drainage system that feeds into the McMurray system, while this system here is related to the paleo drainage that's on the west side of that zone of flexure in the foredeep. So what we're trying to do is understand what the breaks and what the controls on the accommodation are within this foreland basin system in this area here. And to do that, we should first begin to take a look at what's happening with the basement. This is an HRAM map, a high resolution aeromagnetic map that was put together. And you can take a look at the grain that's associated with that map. And you can see, as you take a look at that in detail, there's a series of northeast to southwest oriented shear zones in the Vulcan Suture, the Snowbird Tectonic Zone, the Great Slave Lake shear zone in through here, and work done by other authors where they've taken a look and created a series of burial history curves. The burial history curves are different within each of those compartments that are defined by these major shear zones. And what this is doing is setting up what we call the piano key effect. As we're loading, because of continental collision, off to the west onto these different compartments, the basin itself will end up being pressed down or loaded at a different rate because of the brittleness that's associated with the basin deposits. So some of them may be relatively rigid and you won't create room. So you'll be on a topographic high. Whereas in other areas, you may be able to press down the basement a bit more and you create more space, more accommodation. And that change in accommodation will control the type of channel system and incised valley system that you're dealing with within these units. Going into a little bit more detail, Marion Warren tied together what was happening in the foothills to an example of these HRAM type of maps to be able to show those units, and then tying it back to work, let's say, that was done by Ross back in the late 90s. We were able to see that these were associated with suture boundaries in the basement. And depending on where you are within those types of units, what we see is that if you're north or south, in this case of the Vulcan Low, you have an area where you have low accommodation because you're dealing with a rigid body versus areas to the north of that where you end up having a more ductile body, a less stiff lithosphere, and you're able to create more space. And that's what's controlling these changes in overall accommodation that's associated with the ISOPAC map that we see within those types of units. So we've identified different paleo drainages. We've identified compartmentalization because of what's happening with the basement. So the question then becomes, how does all of that manifest itself low to intermediate accommodation portion of the basin, in the southern portion of the basin. And this is where we begin to tie it back to the foreland basin and what's happening in that area here. And we take a look at different aspects of that, how that tectonic compartmentalization overprints it, what happens when we're in an underfilled or an overfilled position at a higher frequency or at a higher scale at a hot unit. What happens with that migration of that peripheral forebulge, and what is the scale of that cyclicity as we go along? So we did quite a bit of work on the BQ. The BQ, usually in lower Aptian age, was broken up into a couple of different stratigraphic units. We broke it up into many more stratigraphic units in through there. And I'll show you how we did that in a second. And we came with a very, very complicated paleogeography. Again, this is the Township 1 to Township 40, Saskatchewan border to the foothills. Each of these colors represent a different stratigraphic unit. We defined that stratigraphic unit originally based on work that was done by Dan Pataki. Dan Pataki needed a life. He took a look at 1,500 point counts, thin sections. It's not something that I would do, but that's what he wanted to do. And he was able to show, based on the mineralogy that was associated with those units, that we had two different cycles. Okay, we had a lower cycle, which we termed the A sand, okay, which was a dirtier sand with a lot of clays associated within it, and chert and quartz. And it had argillans and all sorts of other fun things within it. And then an upper cycle where we had a progressive cleaning as we went up, as we went from chert and quartz and feldspars to chert and quartz to just quartz units. And we called that the horsefly, the bat, and the Ellerslie. So this is just a detail of what that A sandstone looked like in through here with these argillans, these clays, because at the time of exposure at the top of the A sand, rains would take the clays on the surface, percolating them down, and they would bridge the pore throats associated within these units. You would get what we would call sucker sands when we would drill it, because the well logs would read it as ineffective porosity, but we thought it was real porosity. And so that you'd have problems getting good permeability. You'd compare that to the cleaner units that were associated with the horsefly, bat, and the Ellerslie. So once we had a series of type wells that we knew what the units were, we brought in another technology utilizing chemostratigraphy. And chemostratigraphy basically is a series of samples. Each one of these little boxes is a sample. We go and we took a look at all the elemental chemistry associated with this, and we began to see major changes. So between the petrography and the chemostratigraphy, we were comfortable breaking up the stratigraphy with these different stratigraphic units. We would analyze the data by different types of ways, different types of binary diagrams, different types of ternary diagrams. So we were pretty sure of that mineralogy. We did that with the coarser grain fractions. We also did it with the finer grain fractions, with the clay stones, and we saw similar types of breakdowns by those units and by the heavy minerals. People have tried the same techniques in the McMurray, but they don't break out the same way. But as I showed earlier, you wouldn't expect them to break out the same way because it's a different drainage system. And so there's no reason to think that they would break out the same way as you go along. We had core available to us, like this 15 of 32 well, which basically showed how, here's the core interval, how those different units actually sat in space. So not only did we know the mineralogy, we also knew the order of the deposition of these units as we go along. So let's concentrate a little bit on the distribution of these units. So we felt pretty comfortable taking out, let's say, the A sandstone, which was that lowermost sandstone. And this was the distribution here you see our cross-section grid below that we're looking at. Wherever there was colored in this diagram is where we actually had in those wells, we had a sandstone. We were able to take a look at it and on detailed work, define 3 different geometries associated with this A sandstone. A sheet-like sandstone, which we call the Carmigay, isolated ribbon channels, which we call the Mesa Incised Valley, and a series of cut and fill deposits, which we call the Valley and Terrace types of units. And when we mapped them, they actually were in specific geographic areas. The Valley and Terrace types of deposits, where you had cut, fill, cut, fill, cut, fill, are very similar to what you see in the Valley and Terrace geometry, let's say in the Mississippi, where you had those types of deposits, where you had repeated drop in sea level as you go along through those units. And those occurred normally spatially, within the 4 deep area. The Mesa Incised Valley deposits, the isolated units, usually were on the highs that was associated with the 4 bulge deposits. And to the west, where we had the Carmigay deposits located here, those would be associated with the wedge top deposits. So going back to the foreland basin example, we're starting to see that there's a change in channel systems depending on what type of unit you're taking a look at. If we would then take a look and see what was happening in terms of reservoir quality associated with those different units, we could see that depending on where you were, there'd be significant differences in the reservoir quality, in the core analysis that you were taking a look at. Make sure that you take a look at the axis associated with the permeability, where this was at 10 darcies versus 1 darcy. So the Carmigay, significantly better reservoir quality and much more uniform, little amount of barriers or baffles within it. That was the sheet-like deposits that we saw over here. And you compare that in the 4 deep, where you had these multiple cut and fills, you can see this represented the different cuts of Valley and Terrace and how they were it was a very heterogeneity associated with those types of units. So if we took a look at what was happening in terms of the distribution, this is where we ended up having our Carmigay, the wedge top types of deposits, the sheet-like deposits that were formed south of the Vulcan Low, okay, that compartmentalization associated with the basement. This was cut out by later horsefly, so that's an erosional remnant. We had on these highs here, that's the most western of them, and you could put another one here. That's where we had the Mesa Incised Valley. Those were in the 4 bulge type of deposits, and in the 4 deep deposits, that's where we have our Valley and Terrace type of units. So as being able to be used from a predictable point of view, by knowing that and how it relates to it, we're able then to know what we're going into when we're going into an area. We did the same thing with the horsefly, which was present just to the south of the unit. But what I want to concentrate on in what was happening with the bat type of unit, where we had that nice, well-developed unit that went from southern Alberta up through Crossfield and through there, that was on that zone of flexure. And this was in the area here where we had high accommodation, which was north of the Nick Point, but west of the zone of flexure in through there. And that's when we began to get relatively thick sections of both Bat and Ellerslie associated within those units. So instead of having areas where we had low accommodation and we had sheet-like deposits at the base of a thick incised valley that could be up to 50 to 100 meters thick, we ended up having isolated channel systems within within multiple Paris sequences of estuarine mudstones located in through here. All of this capped by the ostracod in through there. So what we end up seeing here is we have the forebulge breaking out the two paleodrainages. We have the four deep, but here the four deep is changing from low accommodation to high accommodation as we get into those types of units as we go along. The Ellerslie had the same morphology, so the zone of flexure or the forebulge doesn't change that much, but we do flood back. The yellow in through here represents the axis of the bat. The color zone represents what happened when we flooded back during a time of transgression to high stand, and we flooded back into that valley system. So again, we can predict that as we go along in through here. And then the whole thing is capped up by the ostracod as we go along through here, where we have these zone of flexure. The white areas, in this case, represent where we ended up having paleosols associated with the ostracod. The blue areas in through here represent where we have the more calcareous ostracod in through there. And what I'm trying to get here is that there was a change in flexure and isopac so that we can have multiple zones of flexure, or we may have changes over time of where the peripheral forebulge was sitting within these types of units. So we do have good accommodation controls associated with these types of units. We see the change based on the basement of low to intermediate to high accommodation. We see the drainage divides, and we see the paleo drainages, the channel systems that are associated with these. What does that look like? What does that look like when we take a look at it in terms of a cross section? So these are cross sections that were built while we did these studies by Lauren Rosenthal, who took the detailed work that the group were working at, and these represent the different type cores that we have through the area. This is a cross section south of the Vulcan Low in the area of low accommodation. We're sitting on the Jurassic up to this point here. Then in Saskatchewan, we call it the Success. In Alberta, we call the orange the A sandstones as we go along. And you can see that the A sandstones are actually on the topographic highs. They're preserved in the highs, whereas the horsefly bat and Ellerslie erode down into those types of units. We have the Sheet Lake Carmangay, which is sitting out here on the west side of the unit on the high. And the Carmangay, therefore, is interpreted as being part of the wedge top deposits as we're going along through here. Whereas in the area where we're past the back bulge and we're on the craton, where we call it, what it's called in Saskatchewan, we would call that the Success in through there. So it's in a different tectonic setting as you go along through there. Whereas the four deep and the four bulge is the area where you, in the area of low accommodation, is where you had erosion, and that's from the higher cycle that's operating within the unit. North of the Vulcan Low, we have, as we went from west to east, we had an increase in accommodation. So, tens of meters here, 100 or so meters here of thickness. As we go along, again, we see a remnant of the wedge top located over here in orange for the A sandstone. By the time we get over here, we're in the back bulge area, and we're starting to see the change in paleo drainage when we're associated with the forebulge located here within cycle 2. And in cycle 2 here, we get those thick packages of Bat and Ellerslie mudstones with isolated incised valleys like the Penhold incised valley system located in these types of deposits. So to try to pull this together, what we're trying to show is what's happening and what's the distribution of the different units in relation to the foreland basin model. We know based on the chemostratigraphy and the petrography that we have a couple of different cycles. We see that we have different types of channel systems in through there, and it's organized in this unit. But in this case, if you go with the foreland basin model, the A sandstone would be what you'd expect to have in an overfilled foreland basin, whereas the horsefly bat Ellerslie is an underfilled. This is a higher frequency event on an overall larger foreland basin system. So this goes like those nested dolls, like those Russian dolls, a doll within a doll within a doll. There's a cyclicity going on here that occurs, and this type of change may be what's happening. And we didn't do the work on it, but I'm supposing on this is that you have higher frequency accretion events occurring as you're getting the thrusting occurring off to the west. So there's a higher set of frequency events on the bigger scale events. And one of the reasons why one would say that is trying to map out what's happening with the peripheral forebulge. Now, people like Octavian up in U of A and Andrew Mile at U of T and their grad students up in the Upper Cretaceous have been able to show what's happening with this forebulge at different stratigraphic units and how it is migrated through time from going from west to east, and that there are shifts that just happen to be synchronous with changes in the basement, just similar features like the Vulcan Low or the Snowbird Tectonic Zone or the Great Slave Lake Shear Zone. Now, in what we've shown, if you follow that zone of flexure, which in fact is the peripheral forebulge, we see the same sort of thing happening. And so within cycle 2 itself, what we're seeing is a 5 to 7 township or a 50-mile shift in the peripheral forebulge or the drainage divide as you're going along within a cycle. So there's high frequency events going along through those types of units as you're going along. So that sort of makes sense. So to tie this all together, on the big scale in through here within a foreland basin setting where we have this type of geometry, we have the asymmetric geometry that's associated with it. On the gross scale, there's an axial drainage and a transverse drainage that operates in the unit. And where you have axial drainage going from south to north, we're associated with the underfilled portion of the larger scale event that's occurring. And where it's going from west to east, you're in the overfilled portion of it. We can take it along the entire north to south transect of the foreland basin, and wherever we're crossing a major basement feature, like a suture of basement, we would have differences in up and down movement associated that controls accommodation. And within each one of those, you may have higher frequency events and change in the amount of accommodation, which controls the overall or the larger scale drainage patterns. If you take a look at the detail, because I'm going from the big to the small, if you start to take a look at the core and you take a look at the logs and you take a look at the petrography and you take a look at the chemostratigraphy, you take a look at the detrital zircons that are associated with these types of things, you're able then to be able to map out distinct paleo drainages that are operating within these units. The key to all this is that by doing that, one shouldn't expect that one model fits all. when we're taking a look at this stratigraphic zone across the Western Canada Central Basin. The other point being is, if you go into this type of detail within these types of units, you can do that. We've just done this for one formation, for the BQ. You could do the same sort of work for each one of these different stratigraphic units, and then get into a predictable setting where you begin to understand where different play types may sit in time and space across the basin. And what we're trying to do here is understand what is the axial drainages and what are the side drainages operating either in an overfilled or an underfilled component of this type of unit. And then you can start to play games of, are you dealing with the tributaries? Are you dealing with the trunk systems? How these units are moving over time and how they're moving stratigraphically through that as you're going along. So to summarize at the end, what I tried to show is what happens with foreland basin, the fourfold change, what is underfilled versus overfilled units, the cyclicity that goes along with these types of units, how we can apply them to a specific unit to see what's happening as it goes along, what type of techniques that you could use as you went along, and how it allows us to understand compartmentalization that goes along through these things. The last slide that I want to say is just acknowledgements. I got out here in 1981. I started working, so I've been out here. I'm older than I look. So been here for a bit of time, and been extremely lucky to work with some excellent people. This is just a partial list of the people that we're taking a look at, and like anything else, it takes a community to raise a geologist, sort of thing. And all of these people in one way or another have had a major impact over the last 40 odd years in trying to understand what's happening. And I think it's detailed work like this that if we did it on other units within the basin, we'll get a good understanding of what's going on. Thank you.